Okay, so we are going to start chapter 8, and this deals more with some probability issues. And before we start doing some actual probability, we're going to talk about probability distributions. All right, so the first thing you should know is what a probability model is. And that's basically describing all the possible outcomes and the chance process, or how likely it is for something to occur. So if we were talking about a probability model for flipping a coin, if you were talking about, say, the number of heads, and the probability, this is normally how a probability model is. So you could either get 0 heads if you flip a coin, or you could get 1 head if you flip a coin. And the probability of each is just 1/2, because if you got tails, that would be 0 heads, and that would be half of a chance, or 50%, and 1 head would be 50% as well. So a probability model usually looks something like this, and of course it can be longer. We may have more options, and the probability down here always needs to add up to 100%, or 1 if you're just doing fractions, like 1/2 plus 1/2 is 1. So here's another probability model. This time it's flipping 3 coins, and if you remember from our review, we did this one on the board, and we basically said since there's 2 coins, or 2 options, and we're flipping a coin 3 times, we know there's a shortcut to figure out how many there's going to be. So 2 times 2 is 4, 4 times 2 is 8. So 8 is going to be our denominator. And we figured out all of these, and so I listed them out for you. And X, or capital letter X, is a random variable. That's different things that could take on the number of heads. So X could either be 0, 1, 2, or 3, because you could get 0 heads. Like say tail, 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 tail has 0 heads. You could get 1 head, like this one right here, head, tail, tail. You could get 2 heads, like tail, head, head. And you could get 3 heads, which was right here. And then basically to get this probability model down here, they just counted how many times that happened. So with 0 heads, there's only all tails. That's only 1 of those. For 1 head, remember this one counts, this one counts, and this one counts, so that is 3 out of 8. For 2 heads, this is 1, this is 1, and this is 1, so there's also 3 out of 8. And then of course all 3 heads, there's only 1 option of that. And so look at, once again, our table of outcomes. 1 plus 3 is 4, 4 plus 3 is 7, and 7 plus 1 is 8, so 8 out of 8 is 100%. And so if you've done your probability model correctly, like I said, everything down here should add up to 1 or 100%. Now once you get your table, you can make a histogram. So the table was what we saw back here on this slide. This is our probability table. And a histogram is based on the probabilities of each occurring. Okay, so for our coin outcomes, you know, with 1 head, 3, 3, and 1 is how many we actually saw out of 8. So this one, they just did counts on the y-axis. So we saw 1 of all 3 heads. We saw 3 of 1 head, 3 of 2 heads, and 1 of all 3 heads. So we created our chart this way. Another way you could have done that chart was based on probability. So once again, if I wanted to create my chart again, a new table, if I said 0 heads, 1 head, 2 heads, and 3 heads, 1 out of 8 is 12.5%. So maybe this is 10%, and 20%, and 30%, and 40%. I don't think it's going to get much higher than 40. So when I do 1 out of 8, on my calculator, I get 0.125, which is really 12.5%. So that means 0 heads needs to go up to about 12%. Then 3 out of 8 was my next one, and that's for both of these. They both were 3 out of 8. And when I put that in my calculator, I get 0.375 or 37.5%. So it's almost up to 40, but not quite. And there's my beautiful graphs. I know you guys appreciate my drawing skills. Wow, that's amazing. And then, of course, 3 heads is going to be also at that 12.5%. And so this just gives you another option. Remember, this one was counts of how many we actually counted, and then these are based on percentages. So about 12% and 37% was our 2 values. And so our graph looks the same. The only thing that changed is this. And the problem on this graph, I did it on the computer, but I forgot to label the axes down here. So you want to make sure you label down here as well, because this would have been a no-no and would have got points taken off. Alright, so here are some terms that you need to remember. First of all, a random variable is just a numerical value that describes an outcome of some sort of random phenomenon. So our random variable in that example we did was the number of heads, because it could have been 0 heads, 1, 2, or 3 heads. It could take on any of those. It could take on just 1 if I just happen to do 1 trial, but it can't go past 3 heads if I'm flipping 3 coins, because how would you get a 4th head? That doesn't even make sense. And it can't go lower than 0. You can't get a negative number of heads. It's just going to fall within that range. And probability distribution, that goes back to our table that we had right here. This is an example of a probability table or probability distribution. And that just basically gives the possible values for the random variable. So in our case, the possible values were 0, 1, 2, and 3 heads. And then the probability that goes with each. Once we have our probability table or probability distribution, we can graph it, which is an example like I did. So far all we've done is working with heads and tails and different things like that, but you could do random variables with anything really. Let's go over some more terminology before we move on to some new examples, because I want to make sure you guys get all of this. So here are some. This is going back to our probability distribution of flipping a coin 3 times. So if you remember, if we had 0, 1, 2, and 3, and our probabilities were 1 out of 8, 3 out of 8, 3 out of 8, and 1 out of 8. And we're going to use this to answer questions. So if I asked you, what is the probability that x equals 1? Basically, I'm saying, what's the probability that you get 1 head, because your x's are on top and your probabilities are on bottom. So the way you read it is whatever's inside, you come up here, and to get the p, you just drop straight down, or you might have to add some depending on how it asks. But because it just wants the probability of x equals 1, you come straight down, and it's 3 out of 8. Super easy. Now, if I use the symbol greater than, that basically means I want everything bigger than 1. So in our example here, everything bigger than 1 would be 2 and 3. So if you notice, there's 2 probabilities down here, and we're just going to add those together. So 3/8 plus 1/8 is 4/8, or you could reduce that down to 1/2. And once again, if you like decimals better or percents, you could go ahead and change it. We already know that this was 37.5%, and we know 1/2 is going to be 50%. So notice when it said x greater than 1, we don't actually count 1 because it doesn't have that little happy bar under it. Now, the next question does add the little happy bar, and now it says, hey, what is the probability of you getting 1 or bigger? So now we have to add all 3 values together. So 1 or bigger now joins these together. So we already know that's 4 out of 8 plus 3 out of 8 is going to be 7 out of 8. And once again, if you like probability or the percentages better, that would be about 87.5%. So all of this information is coming from our table. I could use the less than symbol as well. If I said what's the probability that x is less than 2, Less than 2 means don't count 2, but everything's smaller than it. So 0 and 1 is less than 2. And once again, 1/8 plus 3/8 is going to be 4/8, or 1/2, or 50%. So there's a lot of ways that they could ask these questions, and basically, like I said, the top row is always your X and the bottom row is always your probability, and you basically just look through it and decide what numbers are they asking for, and then you add the probabilities together to get the final answer. Alright, here's another example. APGAR is a score that they give to newborns at the hospital when a baby's first born to decide how healthy it is. So those of you who want to be doctors, you are probably going to hear this score, especially if you end up being a doctor who works with babies a lot. So an APGAR score is between a 0 and 10, and a 0 is very, very bad, it's not good, and a 10 would be like a perfect newborn. And so if we were to graph this on the board, our options are 0 through 10. And our probabilities, if you notice, they're not very big. The biggest one is 43%. So maybe I'll put 40% up here. This could be 30. This could be 20. This could be 10. And then down here is really, really low ones. So for 0, it's a probability of 0.001. Or basically 0.1%. That's a very low percentage, so we're going to make that a really low bar. For a score of 1, that's probably 0.6. Once again, really, really low. 2 is 0.7. It's really low. 3 is 0.8. So really, you can't tell a difference down here. Fortunately, this is a good thing because these babies are about to die or not going to last very long, so you don't want to see a very big value over here. This one's 0.12%, then 0.2%, 0.38. All of these are really, really low. And then we jump up to 32%, which is right around here. 43% is going to be kind of above our graph. And then 5% will be about halfway up between 0 and 10. So actually 7 should be a little bit taller. Alright, so that's what it looks like when we graph it. It doesn't have to be perfect, but it does need to be labeled. These are your X values down here, or the number of scores that you could get. And then over here is the probability, and that's how it always should be. Alright. So if I asked you what is the probability that you got an X score or a APGAR score of 8 or better, that is what greater than means. So 8 or better would be 8, 9, or 10. So we come down here, and these aren't fractions, so we're just going to add the decimals. So 0.319 plus 0.437 plus 0.053 is 8 or higher, and that's going to be 0.809 or 80.9%. So as you saw on our graph, a big chunk of it is over here on these last 3, which is good because that means these are all healthy babies, which is a good thing. Alright, a probability of X being less than or equal to 5, these are not so healthy babies. We have to find 5, and the bar is under it, so it means count 5. And we're going to add everything basically from 0 to 5 underneath. So the 001, the 006, 007, 008, 012, and 020. So we're going to add all those. And so when I add all of those together, I get 0.054, or only about 5% of babies. So once again, this value right here, these are obviously much bigger than what they should be, but I couldn't make them much smaller with this pen. Very, very low number of children who are in this range. Probability that x equals 7 is easy. You don't have to calculate anything. You just go to the chart and look down, and that's 0.099, or as a percent, that's 9.9%. A healthy baby is supposed to have a score of 7 or higher, so find the probability to find a healthy baby. Another way to write it is to write it in between values. So if I'm asking what's the probability of x being between 7 and 10, I would just add up 7, 8, 9, 10, and I would get those values. So 0.099 plus 319 plus 0.437 plus 0.053 gives 0.908, or 90.8% of kids are healthy, which is good. We want our kids to be healthy. Alright, so hopefully that's pretty clear. This is not very difficult stuff. We just graph it, we have a table, and then we answer the questions. We just have to remember which way is greater than and which way is less than, so that we are actually answering the correct answer. Alright, so now statistics starts to get a little bit fun. We have something called expected value, and this is based on gambling. This is why we have expected value. So this basically combines probability and expected gains or losses that you're going to have over time. So after a while, you start to see some trends. You start to see when you win a game more frequently, when you lose a game more frequently, and we can actually sit down and calculate what our average expected loss or average expected gain could be. So this is super important in obviously gambling, but also in things such as, you know, car insurance. Like, how much should they charge a teenage driver? How much should they charge an adult driver? How much should they charge a senior adult? You know, so they take a look at the expected losses that they're going to have and how likely that's going to be, and that's how they come up with our insurance rates. Alright, so say like you were going to play a game, and you could either lose $1, which up here our x value is -1, or you could gain $1, which is +1. And the probability that you lose $1 is 20 out of 38, and the probability that you win $1 is 18 out of 38. So you might be able to guess that if you play this game a lot, you're going to end up actually owing money, because the probability of you losing is slightly higher than the probability of you winning. But you know, people who gamble know that it's true. They know they're going to end up losing money if they play a lot of times. So they think, well, what if I just play once? Or what if I just play 10 times? So what we're going to do is something called expected value. Expected value is very easy. So expected value, you have your table of values and your probabilities. So I'm just recopying so I can actually write on this. The way expected value works is you multiply down and then you add across. Okay, so multiply down, add across. And so -1 times 20 over 38, hopefully you know, is just -20 over 38. And we have to multiply down here as well. So 1 times 18 out of 38 is 18 out of 38. So if I combine those, it's -2 out of 38. Okay, well, I don't really know what -2 out of 38 means. So you can plug that in your calculator. And you get that that's really equal to -0.0526315, and it keeps going. Okay? Now, the important thing to know is that expected value is not a percent. So please don't tell me that's 5%. It's not, because that negative sign. Expected value is how much money, in this case, you're going to win or lose if you played this game tons of times. So on average, I'm going to round it to the nearest hundredth because it's money, you would actually have -0.05, or in everyday language, you would expect to lose about 5 cents if you were to play this game over and over again. And I actually write this out down here. So if you were to play this game over and over again, you would expect to end up owing 5 cents. So when I ask you to do an expected value, we multiply down everything first. Then we add across. So that's what we're remembering here. We multiply down, add across, and we get a value. We remember that this value is not a percentage. So please don't write that as a percent ever. Expected value is not a percent. Then we sit down and we have to translate what that means. So what does it mean to have negative 0.05? In this case, we were talking about X as a money amount. So if I talk about the expected value as money, then I have to write my answer as money. Expected value is not always money. Sometimes it's talking about number of accidents, or sometimes it's talking about number of children that parents have. And in that case, you wouldn't say the expected number of children I have is $50. No, you would say the expected number of children I have, well, hopefully it's not 50. Let's say, 2 kids. So that's how you would interpret it. So you always want to make sure you look at your X value or your top and make sure it makes sense what you're saying as your answer. And don't just always say it's going to be a dollar amount, because it may not be. Expected value is also, by the way, a mean or an average value. So basically we're just taking the average amount of money you're winning and losing, and that's what we're talking about. All right. If you were to go back to our APGAR example, you would go through and do 0 through 10 and multiply straight down 11 times basically, and then add across. And I'm not going to do that because I don't have a calculator on my screen, but I did calculate it for you, and it was 8.13. So you could go back to this video right here and pause it and calculate it and see if you get that 8 point something number. Multiply straight down and then add across. And you should get 8.13. Alright, let's do another example. So now this is the number of people who live in a house and the probability of each occurring. So first of all, we want to sketch a histogram of our data. And basically they just did the number of people living in a house is 1 through 7. Obviously there could be more than 7 people who live in a house, but they just went ahead and did that. And of course you're not going to have 0 people living in a house, because then we just wouldn't count it. Alright, we take a look at our highest value. Our highest value is 32%. So maybe I'll make my highest value 30%, and we'll just go slightly above that. So for one person living in the house is 25. And maybe you noticed that I am not making these bars touch, okay? Our bars are not touching because these are not continuous data. You can't have 1.7 people living in a house. So the bars aren't touching. 32 is the next percentage. Number 3 is 17 people, or 17%, not 17 people. So just about 20. 15 is for number 4. 7% is 5 people. 3% is 6 people, which is how many people live in my house. And only 1% of people, and I really can't make it much different than the 3%, I'm sorry. But really this bar should be slightly taller than this one. And that is our histogram. Once again, notice that the percentages are labeled on the y-axis, and the number of people is on top or bottom, because that is what our x values were. So this was number 1. Number 2 asks to calculate and interpret P, or the probability that x is greater than 2. Well, the probability that x is greater than 2 is everybody this way. So 2, 3, 4, 5, 6, and 7 people in the house. So actually I have to add all of those numbers down below it. So 0.32 plus 0.17 plus 0.15 plus 0.07 plus 0.03 and then 0.01. All of that together is 75% of the people. You may also have found a shortcut. 25% of people have one person living in it. So 2 or bigger would just be 100% minus 25%, which also gives you 25%. Interpret what this means. 75% of all households 2 or more people in it. Alright, so that's interpreting it. Number 3, find the expected value of x and explain what it tells you. Once again, expected value, we're going to multiply straight down all of these numbers. This is what we're doing here. So, let me give some more space. So, basically, for the expected value of x, we are going to do 1 times 25% plus 2 times 0.32 plus 3 times 1/7 plus 4 times 15%, 5 times 0.7, 6 times 0.3, and then 7 times 0.1. Alright, so bear with me real quick while I stick this in my calculator. Use parentheses when you're typing it in your calculator. It makes it a lot easier. You don't want to make a stupid mistake and have to retype all this nonsense again. And what I'm typing is basically the parentheses around what I'm multiplying. So I'm doing 5 times 0.07. I would do parentheses 5 times 0.07, and that's how I'm actually typing it in my calculator. And then the plus sign is outside the parentheses. And almost done. Alright, and I get 2.6. Now, I like this example because remember I told you expected value is never a percent. So it never fails though. Somebody will get this and they'll say, oh, that equals 260%. Yay, I'm smart. No, you're not. That's not a percent. Remember, you can't get over 100. So that is a no-no. We don't say percents are over 100. So what does this actually mean? How many people on average live in a house? So it means basically 2.6 people live in a house on average. It is an average amount because how do you have 0.6 of a person? You can't, okay? But it basically means that it kind of teeters. The balancing point is somewhere between 2 to 3 people, which makes sense. You know, we have a lot of people in the 1 and 2 category, but then we have lots of other households that get added together. So if you could imagine like a teeter-totter, where would it balance? It would balance right around halfway between 2 and 3. Alright, so the law of large numbers is a random phenomenon with numerical outcomes, and it's repeated many times independently, and the mean of the observed outcomes approaches the expected value. So basically, if you could repeat your samples over and over again and calculate the number of people, and you would look at the average would come to be very close to 2.6 people in a household. Casinos, insurance companies rely on the law of large numbers to make sure that they're making a profit. So we talk about law of large numbers. How large is large enough? And that is our question. So we want to make sure that we have enough. When you play at a casino, you don't play enough to use the law. So you could play 10 times, you could play 20 times. Even if you ended up playing 100 times, you're not going to end up seeing the average like you would hope to see. But because the casinos has lots and lots of people playing every day, 365 days a year, they get to see the results of this. And that's why they can use the law of large numbers. Sometimes if you don't know a probability of something occurring, you can use simulations. So simulations are when you assign numbers to mean certain things, and then you use the random number table, and you can do that. We kind of did that a lot in the last chapter, so I'm not going to really worry too much about simulations. Alright, some other things to keep in mind with probability distributions. We did scores on the APGAR. We did heads and tails, flipping a coin 3 times. And then we also did number of people in a household. All of those are values that could happen in a probability distribution. But it doesn't actually have to be a number. It could just be the number of people who say yes to a question. So if you surveyed people like, would you buy this product if we were to sell it for this price? And people would either say yes or no, or I don't know. So we could count the number of yeses. We can repeat this over and over again, asking 100 people each time, and we can start to see a trend of what we may see. This is a probability distribution, but it's using a proportion of people who say yes instead of like the number that you get on a dice. So you can do proportions. Now, it turns out we studied the normal distribution, I'm going to say in chapter 2 or 3. That was that whole thing that looked like this. It looked like a bell. You guys remember studying this? It turns out that our probability distributions start to take on the shape of the normal distribution again. It is centered around our mean of 0 and within 1 standard deviation. Remember that this was 68% of the data, and within 2 standard deviations it was 95% of the data. And then, of course, within 3 standard deviations, hopefully this is ringing a bell for you guys, that was 99.7% of the data. So we can use our z-score once again. Remember, z is x minus x bar over standard deviation. We did this a long time ago, but you still have to remember it. Okay, because this is very fundamental in statistics. We have to know the bell curve, and we have to remember a z-score. And we could use z-score to get some values. Sampling distribution is the sampling of a statistic tells us what values the statistic takes in repeated samples from the same population and how often it takes those values. When we can't find every single value and put it in the table, we would just use a normal distribution. So with the number of people in a family, like, between 1 and 7, you can actually find, those things, because you have either 2 people living in your house, or 3 or 4 or 5. It's not like you have a weird decimal value. You're not going to have 3.7896 people living in your house, or you're a little bit disturbed and we have some issues. So if you have just a number, a whole number, it's very easy to calculate. But what if your sampling distribution is how much rainwater falls? Well, yeah, it could rain an inch, but it could also rain 1.1 inches, or 1.01, or 1.0001. And as you can see, that will get really hard to calculate and do a table and then do all that. So instead of doing the bars like we were doing, we get that bell-shaped curve again. And the bell-shaped curve comes from many values over time. All right, so let's say we are going to ask teens if gambling is okay. And let's say that we're pretending we know that exactly 50% of teens would say yes, it's okay. But we don't know this. This is something we're trying to figure out. So we repeat this survey over and over and over again, many, many times. And we ask teenagers, hey, do you think it's okay to gamble or not? And they would either say yes or no, and we would record their answer. All right, so our normal distribution has a mean, or an x bar, of 0.5, and it has a standard deviation of 0.022. Alright, it says what's the probability that we get a sample with 52% saying yes. So that means our x is going to be, instead of 52, we're going to write it as 0.52. Alright, so if you remember, calculating a z-score is x minus x bar, so we do the 0.52 minus the 0.5, all divided by the 0.022, and I went ahead and calculated that for us at 0.91. And what we're trying to do is find the probability that you get 52% or higher, really. It's not exactly 52%. So if you have a graphing calculator, you could do normal CDF, 0.91, 99, and hit enter. But most of you, I think, did not have that. So we're going to go back to our z-score table. And oh, I got to look it up real quick. There we go. All right, so it was 0.91. So if you remember, we look up here for the first value, or the first value in the whole number. Since the whole number is 0, these are all negatives. Let's go to the positives. So I need 0.9, which is right here. And then the last number is a 1. So from 0.9, I go over to 1. And do you see how it's 86? Alright, so that would be about 81%. Now, this is actually to the left. So remember, if we want to the right, we have to subtract it from 100. So we weren't quite done yet. 81 wasn't the answer. So since we are wanting to the right, we're going to do 1 minus 81%. So it's going to be about 19%. And when I did on my calculator, I got 18.14. So it's a very close number. So either one would have been okay. Alright, so hopefully that kind of refreshes you. Remember our z value, we have to do x minus x bar, enter, then divide by standard deviation. And then we use our table by looking for the first two numbers and then the third digit, and we write that down. And if we want less than, we have the chart already how we want it. And if we want greater than, we have to subtract it from 100%. Alright, next one. We asked 1,500 college students if they applied to more than just the college they attended. And let's say that the true proportion is 75% of students. We assume a normal model. So once again, our x bar is 0.75. Our standard deviation is 0.01. And the x value is based on the question. So I'm going to call this one A and this one B because I didn't mark it. But this one says, what's the probability that you get a percentage of 77 or more saying yes? So this one we want, x is 0.77, and that or more means to the right. So that means whatever I get from my table, I have to minus from 100. Okay? So x minus x bar divided by standard deviation. So 0.77 minus 0.75. And we divide that by 0.01. We actually get a z-score of 2. So a value of 2, we come to 2.0, and we just want the first column. So that's 97.72%. And remember, we want to actually subtract from 100. So that's 2.28%. B, what is the probability that your percentage is between 73 and 75? Alright, so we have to do our z-score twice. So 73 minus 75 over 0.01. It's going to be negative 2. And then this one, 0.75 minus 0.75 over 0.01. Hopefully you don't have to calculate this. That's going to be 0, and anything divided by 0 is 0. So on our table, I need to find a value at negative 2 which is up here. A perfect negative 2.0 is the very first one. So that's 2.28%. And then if it's completely zero, doesn't matter if it's negative or positive, it should make sense that at zero it's 50%. So what do we do if there's two percentages? We're not going to leave it as two percentages. Remember, it's asking what's the probability that it's between those two. So we actually have to end up subtracting them. So we do 50 minus 2.28. Which is 47.72%. And so that's how you find it when it's between two values. Alright, so your homework this time is going to be a little bit different. I'm going to just type a few questions because I don't really like some of the book questions. So, don't do what the website says, because if you go to the website and you download this video and you or this slideshow and you watch the slideshow, it will have homework at the end, but it's not what I want you to do. So when you go into your Google Classroom, I'm going to have a homework assignment typed out, and so I basically want you to just do that and submit it for me. Alright, that is it for today.